Hello, curious minds. Imagine this. Every single second the sun produces enough energy to power everything on Earth, for millions of years. But how does it do that without burning out? Today we're diving into the insane science behind our very own star. At the heart of the sun, around 150 times the mass of Earth is packed into a space smaller than Jupiter. This is the sun's core, where the magic of nuclear fusion takes place. But what exactly happens here? Inside the core, temperatures soar to over 15 million degrees Celsius. That's about 27 million degrees Fahrenheit. The pressure is unimaginable, forcing hydrogen atoms to slam into each other at high speeds, fusing together to form helium. This process is called nuclear fusion, and it's the same reaction that powers hydrogen bombs, but on a much larger scale. During fusion, a tiny amount of the hydrogen's mass gets converted directly into energy, following Einstein's famous equation. This tiny mass creates an enormous amount of energy. Every second, the sun converts about 600 million tons of hydrogen into helium, releasing as much energy as billions of nuclear bombs. And why it doesn't burn out? Well, the sun's core is in a delicate balance. The outward pressure from the energy generated by fusion prevents the sun from collapsing under its own gravity. This balance has allowed the sun to shine steadily for 4.6 billion years, and it still has about 5 billion years left before it runs out of fuel. Now that we know how the sun generates its energy, how does that energy actually get from the core all the way to the surface? Let's take a journey through the sun's layers, where the energy moves through two very different zones before it finally reaches us. Right above the core is the radiation zone, where temperatures drop to around 7 million degrees Celsius, about 12.6 million degrees Fahrenheit. In this region, energy moves outward in the form of light particles called photons, but it's a slow process. Because the plasma is so dense here, photons get absorbed and re-emitted in random directions over and over again. This means it can take a photon thousands or even millions of years to finally escape the radiation zone. Once the energy reaches the convection zone, things start moving a bit faster. Here, the temperatures are much cooler, dropping to about 2 million degrees Celsius, that's 3.6 million degrees Fahrenheit. The plasma in this region is less dense, so energy can move through giant currents of hot gas. Hot plasma rises toward the surface, cools down, and sinks back down to be reheated, a bit like the way water boils in a pot. This creates massive convection currents where energy gets carried to the surface in big, churning loops. Once the energy reaches the surface, or what we call the photosphere, it finally escapes into space as the sunlight we see. Temperatures here are much cooler than in the inner layers, around 5,500 degrees Celsius, or 10,000 degrees Fahrenheit. It's this light that travels across 150 million kilometers, reaching Earth in just 8 minutes and 20 seconds. So, when you step outside and feel the warmth of the sun, you're actually feeling energy that's been traveling for millions of years just to get here. Now, let's take a closer look at the sun's surface and the layers above it. The photosphere is what we see as the sun's surface, though it's not a solid surface like Earth's. Instead, it's a thin layer of gas, only about 500 kilometers thick. Temperatures here drop to around 5,500 degrees Celsius, or about 10,000 degrees Fahrenheit, which is relatively cool compared to the inner layers. We already discussed granulation, but another cool feature of the photosphere is sunspots. Cooler, dark areas caused by intense magnetic activity. While they look small from Earth, some sunspots can be as large as our planet. Above the photosphere lies the chromosphere, a thin layer about 2,000 kilometers thick. The name chromosphere comes from the Greek word for color, because during solar eclipses, it appears as a reddish glow. Temperatures here increase to about 20,000 degrees Celsius, or 36,000 degrees Fahrenheit, hotter than the surface below. The chromosphere is also home to spicules, thin, jet-like bursts of gas that shoot up from the surface, reaching heights of up to 10,000 kilometers. Finally, we reach the sun's outermost layer, the corona. This is the glowing halo you can see during a total solar eclipse. But the corona has a strange mystery. It's much hotter than the surface. Temperatures here can reach a mind-blowing 1 to 3 million degrees Celsius, or 1.8 to 5.4 million degrees Fahrenheit, and scientists are still trying to figure out exactly why. The corona is also the origin of the solar wind, a stream of charged particles constantly flowing from the sun into space. When these particles interact with Earth's magnetic field, they create the beautiful auroras we see near the poles. The sun's atmosphere is also home to violent solar flares, the powerful bursts of radiation caused by the sun's magnetic fields. These flares can release as much energy as billions of atomic bombs in just a few minutes. Sometimes these magnetic storms get even bigger, causing coronal mass ejections, or CMEs. These massive clouds of plasma and magnetic field can be ejected from the sun at millions of kilometers per hour. When they hit Earth, they can cause disruptions to satellites, communications, and even power grids. And that's how our sun works. But here's something to think about. What if we could harness just a tiny fraction of the sun's energy directly from space? How do you think that would change life on Earth? Let me know your thoughts in the comments below. And if you enjoyed this quick dive into space, don't forget to like, subscribe, and hit the notification bell so you never miss a journey into the cosmos. Thanks for watching. Until next time, keep looking up.